All right, welcome back to System Software, everybody. Today we're going to continue on learning about the basics of compilers, some of the fundamental concepts for compilers. So we're right here. We're just starting the second half of our semester where we're going to learn about and write our own compiler. So some announcements. The online midterms should, I think, be graded at this point. Please come to office hours if you have questions about your grade. Once the makeups are done, we'll release the actual, so you can see the midterm. But I want to wait till the makeups will be different, but they'll be related. So, but come to office hours if you want to see your exam. And I think that's it for announcements. Today, this into postfix exercise is up. I don't think I covered it much last time, but it's just a simple, it's a simple exercise where you hand copy some code, and it's really just to make sure the compiler setup is working for you on Eustace. You have everything set up there. It's like the Git exercise. It's not meant to be challenging. It's just an exercise to try out the tooling that we're going to use for this class. So I have this due on Monday. Let me know if you think that's an issue, because we didn't really go into much detail last time about it. It should be very straightforward. Let me know on EdStem or in office hours if you have any issues with that exercise. We'll explain more about the context of this today, but for the purpose of this exercise, you really just hand copy code and get the code to compile and run. That's really the bulk of what you have to do for this exercise. Has anyone started that exercise? Did anyone start doing it? Okay, some people actually started. Okay, that's good. All right, questions from last time. Questions about proc, which is due in a week from now. Any questions on proc? Any questions on the infix to postfix exercise? On the reading? Any questions on the reading? Who actually did the reading? Okay, so I hope you'll keep up with the reading. There's only 2 more left. This will explain Antler and some of the foundations of these tools. They're can be a little tricky to use, so I encourage you to read over this and do the exercise for sure. And we'll go over some of the foundational stuff today to help explain grammars and parsing frameworks. Questions on projects? Questions from last time? Okay, let's go over the homework. So questions about writing an interpreter like we did in class. Questions about this exercise. So I gave the starter code for this. This is the compiler code. So I gave you the starter code for an interpreter, as well as an algorithm for exponentiation. So all you have to do for most of these operations is just use C's operator, or C's construct for this. So to do multiplication, you would just do the exact same thing as for addition, but use multiplication. And there are many ways you can implement this. This is not the only way. Questions about this homework? Questions on this homework? Yeah.
We were supposed to check for division by 0, right?
Well, it's a good question. Do you have to check for what happens if you do division by 0? Well, but what happens? Did you try running your interpreter?
Oh, yeah.
What happens?
It just says cord down.
Yeah, the hardware catches it for you. So checking whether there's a divide by 0 is not an easy problem to do in general. So you certainly can check, is the second argument given to you by the user 0, and you could check for that. That would be like a static program analysis where you automatically interpret what the program is doing. But if this interpreter, we're just interpreting it on using C's operations, and whatever C does for that, then that's what you're going to get. That's the behavior you're going to get. So you didn't have to check for it for this exercise. That's sort of a bigger question about how do you check for undefined or behavior in languages take program analysis if you want to learn more about that. Another 5,000 level class. But no, you didn't have to do that for this. Any other questions on the homework? So if you've done this, if you've never implemented an interpreter before, you've written your first interpreter. You've actually written a language processing tool if you did this homework. What's that?
Would the language be math?
Yeah, the language is arithmetic. Well, not even arithmetic expression. Single arithmetic operations is the language. But yeah, you've actually written a language interpreter here. All right, other questions on homework or the projects? Okay, in that case, let's do attendance. Okay, so last time we went over some foundations of programming language implementation, the different types of programming language implementation. We compared compilers and interpreters, and we even wrote some really pretty simple implementations of an interpreter and a compiler. But as you saw, the languages, some student actually asked about, the language is pretty simple. It's just a single arithmetic operation. Arguably, you may not need an interpreter or compiler for that. But let's say we want to do bigger languages where you can utter more things, for instance, symbolic expressions. And last time I motivated this problem that we're trying to solve when interpreting languages or compiling, translating languages, with some examples. And I asked you, what does this mean? So what does this mean, these glyphs on the screen, these black and white dots that you're seeing? What does it mean? So someone says it means 7. Someone says whatever you interpret it to mean. So why is it 7? It's 7 because you interpret these glyphs as numbers, you interpret these symbols or glyphs as arithmetic operations, and then you even have some rules that maybe you're kind of implicitly not even aware that you're applying of order of operations. So there's several ways or at least 2 ways to interpret this in math. You can either interpret this as the addition goes first or the multiplication goes first. And so it's kind of hard to tell who's right. If you're looking at an example like this, which was kind of like, I think, sort of a classic example of decisions about order of operations, this slash here, do you interpret it as a line over the entire denominator, or do you interpret it as just division happening here? I don't know of any law of nature that tells you which is which. So you can interpret it in 2 ways, right? You can interpret it as 6 divided by 3, 6 divided by 2 is 3, times 1 plus 2, applying the parentheses first, or you could interpret it as 6 over 2 times 1 plus 2. Some of you may disagree or agree. But to really highlight, because there was only one person who could read the next symbols, for sure, to highlight the fact that these symbols don't have meaning without something interpreting it, like they don't have meaning on their own. So who can actually read this? Who can read this? Okay, so I think the person who could read Chinese is not here this time, but you can infer it, right? So some people can kind of infer it because these symbols actually, they kind of, it's all human language. So the humans are doing this, and you can actually interpret this as like a count, which is, I think, exactly where these symbols come from. These are a little harder to interpret as plus, but this is the Chinese character for plus, and this is the Chinese character for multiplication. So this has the same meaning if you were to translate it to, well, this is not even English. This is like, I don't know, Arabic or Hindu, who knows? But it's what we use in English, and most languages around the world now use these symbols. It has the same meaning. If you ask someone who can read this, who's learned math in these symbols, and you ask someone who's learned math in these symbols, they'll both say this is 7, or maybe they'll say this is 9. But I just want to highlight that these symbols on their own don't have intrinsic meaning. They have meaning because we, as the interpreters, ascribe meaning to them. Questions on that? Does that kind of make sense? Any disagreements about this? Any other views? So this is kind of a philosophical position. It's sort of hard to prove that this is the case. This was a sort of anecdotal proof that at least these symbols don't have intrinsic meaning, at least not all of them, to you. Any questions on this? Thoughts on this? Any arguments about it? Do symbols actually have intrinsic meaning? Yes? So somebody's yes. So there's a classic adage, the map is not the territory. In other words, the map that describes land or the geographical relationships, distances between places on the earth, on the territory, is not actually the territory. So if you redraw, say, a river, the physical river is not going to move. Whereas if the physical mover shifts over time, then we would just call the map wrong, right? So the map is not the territory. And you've all encountered this when you dealt with pointers in C. So the really tricky part about pointers is that the pointer is a number. So the pointer is a physical thing in the machine. But what is the value of a pointer? What is the value of a pointer? Well, yeah, so if you look in the machine, it's a number, and that number represents an address. So if you dereference the pointer, then you get the value of the number that it's pointing at. So you can think of the pointer as like the map, and the number that it's pointing at like the territory. And so this is why I argue that these symbols don't have intrinsic meaning. They don't have intrinsic meaning without something interpreting it. And we're going to use this philosophy in order to have a machine ascribe meaning or be able to interpret or translate these symbols automatically without a human. So, normally when we think of language, we think we learn the language and we can interpret the meaning of those symbols. But because they don't have intrinsic meaning, at least in the machine, how can we ascribe meaning to them? And that's what we're going to do today. We're going to learn about some of the formal framework that we can use to start processing these symbols and start giving them meaning. And in fact, when we write our compiler, what we're basically doing is giving meaning to our input language in terms of assembly language by translating it. So, if you couldn't read these symbols, but you had a translator that could convert it into this, well, then you'd be able to interpret the meaning of it. And that's exactly what our compiler is going to do. We don't have any machine that will process C code, but we have machines that will process assembly. And if we can write a translator, then we can actually run that program by first translating it. Okay, so I think we've gone over ASCII a couple of times. I just want to make a quick refresher on what ASCII code is, because ASCII is how we're going to represent the symbols on our machine. So this is a table of ASCII codes, and the numbers here on the left, these are the integer number, the machine represented integer in various bases. So I'll just use the decimal one because most people know that. Yeah.
Sorry, what was the command you used?
Oh, I did man for man page,
Okay.
and ASCII. So the man pages actually have the ASCII table, which is kind of cool. So it's in section 7, like the information section. So looking here at the second column, decimal, this is the machine representation, in like an integer representation, where you have a sequence of bits. This is the number that we use to represent the character. And in this column, we have the representation of the symbol. So for instance, if we want to represent the ASCII symbol for 1, we use decimal integer 49. Questions on this? And so that may seem a little counterintuitive for the number symbols, but once we get to letter symbols like capital A, well, let's take capital A here. So A is what, 65 in ASCII? There's no number, since the machine is representing numbers, and it's implementing arithmetic and logic on using integer numbers or floating point numbers, then we can't intrinsically represent a character like A or B, but we can just make a mapping from numbers to those characters. And so that's why you just have, by convention, define a mapping from these integer numbers that can be represented in the machine, that are represented in the machine, to the symbols in whatever language you'd like to have. So for ASCII, we've got the Roman letters and the Arabic numerals, along with a bunch of punctuation and some non-printable characters like new line, space. And so this ASCII code, it's not the only ASCII code. Does anyone know any other? Yeah. UTF-8, good, yeah, so UTF-8 is arguably more common. Any others? Anyone know? Yeah. JIS, okay, so yeah, Japanese and other languages that have other symbols that they'd like to encode. JIS is one. EBCDIC was like IBM's competitor to ASCII. But in this class, we're going to be using ASCII. ASCII is small. It's only 120 something, 127, I guess, characters. And our language compiler is going to ascribe meaning to these characters. Okay, so that's ASCII code. So any questions on how we represent symbols in the machine? And this really highlights the fact that this representation really, having number 48 for 0 really has nothing to do with math. It's not going to help us do arithmetic. That's why in our interpreter we had to translate the ASCII number into a machine code number. Okay, but the individual symbols of the language isn't quite enough to help you understand what a language means. And to illustrate this, let's take this sentence. The boy went to the store. So who's done sentence diagramming? Does anyone do this anymore in elementary school? Nobody does this anymore. Okay. So you got to do it now. You got to do some sentence diagramming now. So what are the parts of speech, as used in linguistics, what are the parts of speech of this language? So we've got the boy went to the store. So we know this is a sentence, or we call this a sentence. Who's doing the going here? The boy, right? So we know that this part here, this part is the subject, right? So in English at least, how do we know where the verb is? What is the boy doing? They're going, they went, right? So we have subject, verb, and then object, or in this case, indirect object, but let's not worry about that. So we've got subject here, we've got a verb, arguably went to, maybe might be the verb, and we've got the object, to the store. So now, we as language interpreters, we don't explicitly have to hear, hey, I'm going to tell you the subject, it's the boy, and then say, here's what the boy is doing, going, or went. We don't have to hear any of that. Instead, we know which is which, right? We know where the subject is. We know it's not the store that went to the boy. Why? Why is that? How come we don't have that confusion when I tell you the boy went to the store? Yeah.
Because in English, it's always going to be in this order.
Yeah, the order, exactly, the order. And that order is not expressed anywhere explicitly. So the boy, there's actually sounds that I'm saying and symbols on the screen for boy and store. But the arrangement of the words also conveys meaning. And this is called syntax, when you describe the various valid arrangements and ascribe meaning to those arrangements. That's syntax. Questions on this? So that's a grammar or syntax. Questions on this? Who's learned this before? Who's learned grammar like explicitly? Okay, that's good. So you learned that. You didn't do sentence diagram, but you learned that. Okay. All right, so syntax is how words are ordered, or groups of words. And so in English, at least, one sentence type is subject, verb, object. And so if you're a listener, you will hear that order, and you'll know that it's not the store going to the boy. Now, other languages have different orders, but there are conventions in languages that allow us to to understand this. And of course, we can hear other orders as well. We accept, the boy to the store went, like Yoda or whatever. Latin, Japanese, other languages have this order. And so this syntactic structure captures relationships between words. Now, to illustrate how this is structured, how this is a nested tree structure, so I drew this as a tree. I just kind of did it without telling you. I just said, well, we can break a sentence down into subject, verb, object, and then break each of these down into their component pieces. Well, you can argue that this has this sort of nested tree structure by looking at a sentence like this. So here is the boy, leaving behind his friend, went to the store. So now in this sentence, who is going? Who's going to the store? Who says the boy is going to the store? Who says his friend is going to the store? So nobody says that, right? Nobody says that, even though friend went to the store appears in the sentence. His friend went to the store. That literally appears here. But we don't interpret that as his friend going to the store. We interpret it as the boy going to the store. How could that be? This is a linear sequence of sounds, and somehow we don't lose track of the fact that it's the boy going to the store. Isn't that amazing? Is that not amazing to you? So you probably never thought about this because you just sort of invisibly do this. But one way to interpret this in a kind of way that, so I'm not a linguist, but the Chomsky, who kind of pioneered this style of syntactic analysis, argued that our brains are actually doing something like tree processing, are saving this information in a tree-like structure, almost literally in the brain. And so if we diagram this sentence, what do we get? We get a sentence. We still have an object here, we still have a subject here, and we still have a verb, and we still have an object. And that object is still the store. And the verb, so we have a couple verbs here, right? And we have a subject here. So if the verb here is went, what's the subject of that verb? The boy, right? But we've also have a modifier to this boy part here. And that boy part is kind of like a miniature sentence. The boy leaving the store. It has its own, so I forget the actual, I'm not a linguist, I forget the actual term for this. I think this is some clause or maybe a gerundive or something. I don't know. I don't remember the words for this. But there's a kind of modifier here, leaving behind his friend. So we know just by the grammar, just by the ordering of words and the choice of words using the ing version of this, that these symbols, even though they appear at the exact same level in the same sequence of sounds with the boy went to the store, we know that that this leaving behind his friend, that's modifying boy, and boy is the subject of went. And so in some way in our brain, somehow we are, when we utter this or when we hear it, when we hear the boy and we hear leaving behind his friend, we're in some sense pausing the sentence. We're pausing the boy went to the store sentence for a little bit to go off on this deviation into another clause. And then once we hear this verb, we can deduce, maybe invisibly, maybe implicitly, we can deduce that went to the store is what the boy is doing, not what his friend is doing. Does it kind of make sense? And so you can see that there's this apparent nested structure to language that humans seem to be doing automatically somehow. Now, whether you believe that's completely learned or something built in is kind of an argument in cognitive science or psychology. But we know that this happens. We know that you can at least put this syntactic structure on language. And this structure, this is what we're going to use to start defining our own programming language. So questions on this? Thoughts on this? Yeah?
The sentence would sound less weird if you said abandoning instead of leaving behind.
Oh, yeah, okay. The boy abandoning his friend. Well, that has some connotation to it, right?
Yeah, but leaving behind his friend sounds ungrammatical to me. It should be leaving his friend behind. But
Sure,
that
yeah.
would ruin the example.
Yeah, that would ruin the example. I think that's probably why I did it this way.
Ruin the example, but still make it grammatical.
You could say abandoning his friend, yeah. or ditching his friend, which is the connotation of that. So, okay. And so you could argue that, well, okay, this is kind of a different verb, right? This is leaving. So why would you think why would you wouldn't be confused, right? But to show you that you can't just look at words themselves, what does store mean? If we just take the single symbol store, so here we have the symbol store, the exact same sound, the exact same letters on the page. In one sentence, we have the store is closed, and another we have squirrels store acorns for the winter. So what does store mean? Here. Has two meanings, right? And its meaning actually depends on where it is in the sentence, on the arrangement of words. So it is literally the same symbol, but we interpret this symbol differently depending on how it's used grammatically. So here it's used as what? What's the part of speech it's being used as? Oh no, grammar school doesn't teach grammar anymore, I guess. It's a noun, right? It's the noun. So it's a noun. Nouns are for objects, nouns are for things. So the store is closed. So the store is the subject of the sentence, and it's a noun. And here, what part of speech is it here? Verb. Yeah, it's a verb. It describes, actions. So squirrels store acorns for the winter. So this is literally the exact same symbol, but it has a different meaning depending on its grammar structure. So just to kind of emphasize that the meaning of these things depend on their structure. So if we go back to arithmetic expressions, then we can start to see how we can kind of define the meaning of this. We know the meaning if we have learned this already, but how can we define computationally or algorithmically the meaning of this expression? We can start breaking it down into this syntactic structure. So let me diagram this sentence. So this may not, this is not a sentence in kind of the traditional sense, but we can treat this as a language just like we treated those English utterances I had before. And so here's how we can break down arithmetic expressions. We can say, well, we've got an expression, and on one side we have, let me do this from the bottom. So we've got an arithmetic expression here that consists of a number, an operator, and another number. So that makes sense, right? So we can say, just like we had sentence or noun or subject, we can say this for math. We can say, well, here's an expression. Expression can be, if we have a number followed by an operator followed by a number, then voila, we've got an expression. And we can use, the kind of, so we can just assert that these symbols are the ones part of our language, that are part of our language. So there's our numbers and operators. And we can say if you put these symbols in a specific arrangement, if you put a number followed by an operator followed by a number, well, that's a math expression. And math expressions, you can have many, many operations in the same math expression. And what does it mean? Well, one way to interpret it is that we compute 9 plus 3 first, right? And then we save that value, and then compute the subtraction using that value, right? That's how you would calculate a long math expression. You would take 9 plus 3 and say, okay, 9 plus 3 is 12. So let me save this using a different color. So let me save this as 12. And then I'd take that intermediate value that I computed and I'd do the subtraction, 12 minus 2, and say, all right, well, now we've got 10. Right? That's how you would compute an arithmetic expression. And we can capture that structure using a tree, just like we did with sentence diagramming. And so here is an expression tree for this arithmetic expression. And this even lends itself to an algorithm, a strategy for doing an interpreter of this language. So for our interpreter that we did last time, we just had single arithmetic expressions. But what would we do if we have this nested structure? So what's an algorithm that you might think of, that you've seen in CS1 for computing the value of this expression? Yeah.
Converting into postfix.
Okay, you could compile it, right? You could translate it to postfix, but then you need to interpret postfix. So okay. So that is one way, and actually, you're going to do that for your exercise. You're going to convert infix to postfix. So what's a way that without having to translate, we could directly interpret? Yeah, what's an algorithm we could use? I think you had, yeah, good. You could use a stack. Okay, well that's what you do for. Yeah, you could use a. You don't even need to use a stack. There's even a way. Yeah, go ahead. Yeah, post order traversal. You can do a tree traversal here. So stack you can use to interpret postfix once you have postfix. Yeah, you could do it here as well. It's called you'd have to do parsing first though. But assuming you have this tree already, you've already learned the algorithm for evaluating this, and that's a post order traversal of the tree. You just traverse the tree. And so evaluation, once you have the tree, once you know its structure, you can just do tree walking to evaluate and interpret the meaning of the symbol. So you can break down the meaning of a language as what's its syntactic structure and what's a traversal algorithm that will compute the result of that structure, compute the value of that structure. And that is basically the definition of a language, at least the definition we're going to use for this class. So let's see what that would look like. So let's take our symbol here. So we'd need some way to, let's assume that we can, we already have a way to convert 9 into the integer 9, which we saw in our interpreter already. So how would this work? So we start here, and how does post-order traversal work? You first evaluate both children. So we evaluate this child, but how do we evaluate it? Well, we can just define a rule that says whenever you see, you evaluate the left child, and so we just convert that to integer 9. You evaluate the right child, convert that to integer 3. And once we have the two children, and we have an operator, we just convert this ASCII symbol, because remember, this is not the math symbol for plus, this is just an ASCII symbol. It could have been a Chinese character like I showed before. And the algorithm here is once you've reached the root again, you just take the value of the two children and perform the addition. You actually do add of 9 and 3. So this represents the actual computation. This is using plus in C, or doing plus in the processor. You see what I'm saying? So when you do this computation, you find that the value of this child, this node, is 12. You see that? See how that's post-order traversal? Compute the value of the left child, compute the value of the right child, and then compute the value of the parent. And so now once we have this value, we can continue with the root of the tree, to continue with this parent. So to find the value of this leaf node, we just convert the ASCII symbol to the real math symbol. So here in green, this is like our integer symbol. Blue is our ASCII symbol. And now we've got a subtraction expression here. We have the value of the left and right child. So we can compute this by using the actual math operation for subtraction to give us 10. Pretty cool, right? So you can frame language interpretation, and as we'll see, language compilation and translation, as just tree traversal algorithms. Because the tree actually captures meaning in the syntax, Because as we saw, the arrangement of words also defines the meaning of a language. Okay, questions on this so far? Excuse me. Okay, so we have interpreted the meaning of this language, by just performing the computation to give us the resulting value that, according to the definition of arithmetic expressions. But how can we determine the assembly code version of this? How can we translate this to assembly or to postfix even? What's the assembly code version of this program? So we saw this last time. What would we have to do in assembly to to compute this exact expression, assuming that we actually do two operations, right? So in assembly, we can only do a single add at a time, right? So let's use a MIPS-like, I'll use an x86-like language. So in order to do this in an x86-like language, if we actually want to do the operations, we'd have to, one way to do this would be to store these values in registers. So this is, I'll put arrows here to make clear where the storage is going. And then perform the addition, which will store the value in A. So that's how addition works in the assembly world. And then we'd have to do another computation, right? We'd have to somehow use maybe another register or reuse B. And we'd have to perform two operations separately, right? So there's not a single expression in assembly that will compute this for us for arbitrary, including variables for arbitrary symbols here. We have to use multiple operations. We have to tell the processor to give us multiple operations. So in the same way that we interpreted the meaning of this tree, we could also use this tree for translation. We can use this to translate this code into machine code. So let's say we take our expression tree again. We take our expression tree again, and we have this evaluation strategy. Looking at the leaf nodes, whenever we encounter a leaf node, we just have a rule to translate that into the language we're targeting. Whether that's math and translating it into a machine code number, whether that's assembly. We translate the leaf nodes, have a rule for translating them. And the inner node is the result of the operation on these child nodes. So if we wanted to translate this code instead, we could say convert this 9 into the assembly immediate value for 9, convert 3 into the immediate value for 3, and then the result of plus would be generating assembly code. So this gives us the same kind of result we saw. This gives us the same kind of result we saw with our compiler last time, where we performed the, so I'm running out of space. So don't worry too much about what the exact assembly code looks like. But in the same way that in green here, we put the value of the computation, we could define it to be more code that we generate instead. So instead of trying to directly compute the value of this tree, we can treat the value as a translation to another language. So whenever we do the same post-order traversal, and whenever we see an expression node, instead of computing the addition, we spit out assembly code. And that's what a compiler does. That's what a compiler does. It takes the input language and it interprets the meaning of it by generating this equivalent code in a new language. You kind of see the point here? Where previously, when we reached an expression node, we directly computed the value of this node. So we discovered that this node's value is 12. In the case of compilation or translation, instead of trying to figure out what its resulting value is, we produce code in assembly that will compute the value of this subtree. So that may not make much sense for 9 plus 3, but once we get to this tree, once we get to the parent tree, and we also have to generate some code and do the subtraction, then the tricky part is generating the entire sequence of assembly that has the same meaning as this in our math expression language. Okay, so questions so far? I'll show more examples of this. I'll make this a little more rigorous and clear. Questions on this concept so far, that we can get the syntactic structure of a language and then do tree traversals in order to figure out what the meaning of that is, and even translate to another language. Okay. All right. So let me highlight one other point when it comes to these syntax trees. And that's the problem of ambiguity. So if I use this same strategy to find the syntactic structure of this expression here, 1 plus 2 star 3, what would the syntax tree look like for 1 plus 2 star 3? What's the syntax tree look like? So if we use the same syntactic structure we had with our previous expression, what's the syntactic structure of this tree? Or another way to say it is, yeah, go ahead. Okay, so one way to draw an expression tree for this expression is to have 1 plus 2 under its own expression subtree, and then have a parent tree for the expression computing the result of 1 plus 2 times 3. And so what, if we use our interpreting strategy, a kind of intuitive interpreting strategy, what value do we get when we compute this tree, when we interpret this tree? 9. You get 9, right? Because if you use our evaluation strategy, our post-order traversal, you get 3 here, right? Because you do the addition first, basically. And then you do the multiplication, giving you 9. But without any additional rules about the syntactic structure of our language, there are 2 ways to draw a tree for this expression. We could also draw a tree like this, where the multiplication happens first, where the multiplication is in its own subtree, and then the result of that multiplication is one of the children of the parent tree. You see that? And so if we use our interpretation algorithm, what is the value of this tree using our interpreter algorithm? 7. So you would, if you're doing post-order traversal, you would compute the value of 2 times 3 first, 6, and get 7 for the tree. And so you can see here, this is how we can make explicit this notion of order of operations. And if we had rules that would define what syntactic structure a language is supposed to have, we could rule out this ambiguity. So ambiguity is when you have multiple possible trees that can represent the syntactic structure of the same sentence, of the same thing. And that's the source of ambiguity in those examples we saw before. So one way to resolve them is with order of operations, which most people use. But with that more complicated example, 6 divided by 2 with parentheses, that's a little bit more complicated to be able to how to express what's the right way to do it. But okay, so ambiguity is when you have multiple trees that you can use to represent it. So let's start to make this a little more rigorous. So this is all kind of intuitive and a little wishy-washy. So you can make the syntactic tree. If you have the syntactic tree, you can do interpretation and compilation. So let's see how we can actually represent these languages. So this is called the parsing problem, the problem of taking a sentence in a language and figuring out what its syntactic tree is, what its syntactic structure is. This is called the parsing problem. And it's challenging for the same reasons that I pointed out, that you have this just linear sequence of symbols, and at least when we interpret language, we can perceive some nested structure to the language, but there's nothing in the utterance, there's nothing in the sentence that explicitly tells you, here's the noun, here's the modifying clause, here's the verb. And in the same way, there's nothing telling you in this sentence here what the order of operations is. There's nothing in the actual utterance that says this goes first or this goes first. So how can we represent these rules. And so what we can do is we can define the syntax of the language. We can define a grammar for the language. And those kind of maybe annoying for some grammatical things like what's a noun, do you have rules about, do you leave a preposition at the end? All of these grammar rules, you can actually take grammar rules, encode them in the machine, and have the machine automatically parse or interpret the structure of a language. All right, so here's some of the formal definition. I'm going to give you the formal definition of grammars and the kind of technical names for these pieces. So to write down a formal grammar, which means you just explicitly state what the grammar is, there are 4 pieces to a formal grammar definition. And this was pioneered by Chomsky. So you have terminals, non-terminals, productions, and the starting symbol. So these words are a little technical, maybe a little esoteric, but we're going to, this is all throughout the compilation literature uses these terms. So let me go through first what these terms are. So there's 2 kinds of symbols in the language. There's terminals and non-terminals. Terminals are the things you actually see, like 1 and plus and multiplication. Non-terminals are the names of the grammar constructs. That would be like noun or verb. And so in the same way when we speak a human language, if I say the boy went to the store, those utterances, those are the terminals. Those are the words of the language. Names like noun, sentence, subject, object, verb, we don't say those things, but we can make those symbols explicit in our grammar, and those are called non-terminals. And productions are the rules that tell you how the sentence structure breaks down for any sentence in the language. Okay, so terminals are the words in the language. This is actually what you see here. So these are like the actual tokens in the C source code or in the language that we're going to interpret. These are like the ASCII codes, ASCII symbols in the language. These are the terminals. Non-terminals are the names of sentence structures, like expression. So if I give you 1 plus 2 times 3, I never say expression. You just interpret it automatically as an expression. But in our tree structure here, notice that in our tree structure, we gave an actual name. We gave a symbol to this structure. This symbol isn't anywhere in the actual utterance. But when we define the tree, we gave a name to the tree structure, expression. So those are the non-terminals. Those are the symbols that define the names of the structures in the language. And productions are rules that map non-terminals, the names of the structures in the language, to the contents of those symbols. So for our sentence example, a potential production or rule that defines the structure of a sentence, we can define it like this. We can say a sentence, arrow, like breaks down into or is composed of subject, object, verb. And so here we have a rule that defines the contents of a sentence, the structural contents of a sentence. And similarly, we could say, well, there's other types of sentence structures. You could say subject, I reverse this. So for English, it's usually subject, verb, object, but maybe you want your grammar to allow subject, object, verb, like Yoda speak, or Latin type sentences. And so we can have multiple rules for the same structure. And that kind of makes sense, because if you have, say, a subject, well, there's many ways to define a subject. You could have a noun, you could have the followed by a noun, you could have a noun phrase. And so we can start building up all of the syntactic structures in our language by defining these rules, these production rules. Questions on this so far? I know this is getting a little abstract, but we'll show a concrete example with math expressions. But this is what productions do. They tell you how a non-terminal or name of a syntactic structure in your language breaks down into smaller components in your language. And notice here that this already starts to imply a tree structure, because a sentence breaks down into subject, verb, object, subject breaks down into one of these choices, and so on. And so this definition of the grammar is what's going to capture all the possible syntactic structures, the trees of our language. Okay, starting symbol is just the name of the non-terminal that you put at the root of the tree, basically. Okay, and we made this clear already, that constructs can be nested. So we can say in our formal grammar things like an expression can be composed of some other expression followed by the plus symbol followed by a number. And so even though we use the same non-terminal symbol, in the contents of that expression may differ, right? So an expression can be a potentially infinite number of possible math expressions. When we go to parse it, there are, or when you go to define that, a grammar for that, well, we can just use the single symbol E as a placeholder for all the possible expressions, all the possible arithmetic expressions. And these grammar rules, or the productions, tell us how to find this tree for each of those math expressions. Okay, so let me get into an actual example of this, and I'll show you how, hopefully, show you how this grammar structure, grammar definition captures the parse trees or captures the structure of these languages. Okay, so here is a grammar for expressions. One grammar for expressions. There's a lot of ways to define a grammar for expressions. This is one way to define it. So let's start with the terminals of our language. The terminals of our language are those symbols that don't have expansion rules. They don't have productions. Usually you just define these ahead of time. I didn't define these explicitly here, but they are the ASCII symbols 0 through 9, as well as the operator symbols plus, minus, star, and slash. So those are the terminals in this language. And an expression can be one of 5 different structures. You can either have an expression is some other expression followed by a plus symbol followed by another expression, or it can be an expression followed by the minus symbol and an expression, etc. Or an expression can just be a single number, n, a single n. And then these pipe symbols here just represent or. So this n can be 0 or 1 or 2 or 3. You can also represent that as just n is 0, n is 1, etc. So that pipe symbol just means the same thing as this. So questions on this? This is our first grammar for expressions. And so this captures this parse tree structure for all grammar expressions. So one way to think of this is a finite definition that captures all possible parse trees for the infinite set of possible arithmetic expressions. I don't know if that helps at all, but anyway, this is a definition of the grammar. This is a definition of the valid word orderings of arithmetic expressions. Questions? Questions so far? Okay, so the problem of parsing is to take this grammar and figure out what this parse tree is. And this is kind of a hard problem. This class is, I think, too short to go into that. Take compilers if you want to learn how parsing actually works. But we're just going to use a parsing framework that will do this for you automatically. It will take this grammar and it'll figure out a parse tree for you for any expression in our language. Okay, so we already defined the. Okay, so remember how intuitively we can define an interpreter as a post-order traversal of this tree. And the way we did that is we said, well, okay, whenever we see an expression, we take whatever the operator is and apply that operator to the value of the two children. Right? And that rule is the same for all the expressions in our tree, in our language. So if we have an expression here, it's the same thing. We take whatever the value of the left side is, whatever the value of the right side is, take the operator and turn that operator into the actual math operation and compute the value. Make sense? So that's how we kind of intuitively defined our algorithm. Now that we have a grammar that defines all of the syntactic structures in our language, we can explicitly write that computation next to each of these structures. So we can say, if we see an arithmetic addition construct, then we do this computation in order to find its value. So let's start with the terminals in the language. So if I've got a symbol n, well, its value is the string 9. So it's still its ASCII symbol. If I see an expression that has n as its child, then the value of that node is the conversion of ASCII code to integers. So let me show this in a more explicit example tree. So let's take our same example, although let me use the same names of the symbols I have in my grammar. So I've got 9. Let me put these lower. So I have 9 plus 1 minus 2. This is what the tree will look like according to this grammar. So I've got at the root of the tree, I have this syntactic construct. I have E followed by the minus symbol followed by E. So E followed by minus symbol followed by E. That's this construct here. And under this E expression, non-terminal, I have the first production, the first rule in our language, E followed by plus followed by E. See that here? So for each construct, I define the computation that you do in order to interpret the meaning of this arithmetic expression. So for and then you can see here that we have the construct n decomposes into the symbol 9. So I can state in my computation here on the right how the value of each of these nodes is computed. So if I see an n, the value of this node is, if I have n, the production says n decomposes into 9, then I set the value of this node to be the string 9. And I can do this for all of the n's in my tree. If I see E, the production E becomes n, here are the structures that match that rule. In order to compute the value of that, I convert the ASCII symbol of n's value into an actual integer. So for each of these tree nodes that match, our this production here, I convert each of those into their actual integer numeric values. In order to compute this construct's value, I find the grammar rule that matches it and look at the computation, the rule in the computation to use to compute the value of this node. And how does it work? It takes the value of the left child and the value of the right child and computes addition on those children. So I have 9 and 1, and the value of this is add 9, 1, which gives us 10. And same thing for the root node. So what production here do I use in order to compute the value of this parent node? I use E minus E, because this is the syntactic structure that's captured by this tree node. And in order to compute its value, I just look to the semantic rule here on the right And it says to take the value of the left child, the value of the right child, and compute subtraction. So I take the value of the left child and the right child and compute subtraction. So we saw this already when we were interpreting the tree, but this is how you can write down formally, explicitly, what those rules are. So we just did that in our head before. We just did a tree traversal algorithm. But this allows us to both take a grammar that defines what the syntactic structure of our arithmetic expressions is, and define rules that tell you how to compute the value of this arithmetic expression once you have the tree, once you have the syntax tree. So questions on this? Okay, so I know this is a little rough. I was stumbling a little bit through there. But I just want to illustrate that what we did intuitively, where once we have the syntax tree, we can compute and value through this tree traversal. We can write down explicitly on paper how that computation proceeds by using this style. Once we have the grammar, we can define a semantic rule or a semantic computation that defines how you compute the value of each of these nodes. And this is one step into turning this language processing into an actual machine, into a program, by taking this definition and just writing it up in code. Yeah?
I guess my question is, why don't we define the grammar normally as E1 or E2, just have everything as, couldn't that get it more confusing?
Well, so if you say E1, then it's like saying noun versus verb. So this captures the fact that, say, there are lots of noun phrases. The boy, the girl, the boy who went to the store. These are all various noun phrases. But they're all the noun phrases. You have one word, noun phrase, to describe all of them. So it's the same thing here. E describes all possible expressions. So if we were to say E1 here, then we would restrict what can come to the left of a plus. But anything can come to the left of a plus, right, in a math expression. Now, there are other ways to write this that, say, preserve order of operations. But this just reflects the fact that you have multiple different types of structures for the same syntactic structure. Multiple different ways to break down that structure. So a math expression can have plus or minus or times or divide. And they can have any other expression on their left and right. Does that kind of answer your question?
Yeah.
Okay, so this is how we can, in terms of a grammar, formally define an interpreter in terms of the grammar. So you can certainly do this by writing a parser and then writing a tree traversal algorithm. This gives us one specification that effectively defines the meaning of arithmetic expressions by combining its syntactic structure definition with rules for computing the value of each of these syntactic structures. Okay, so for defining a compiler, we can do the same thing. We can use the same strategy. For each of these grammar constructs, we can define a rule that computes the resulting value, but instead of actually computing that value using addition and subtraction, we can instead compute a string that represents the translation of these rules into another language. So this is a definition that converts infix notation to postfix notation. You probably did this with an algorithm, a stack-based algorithm, I think in CS1. This is a formal specification of what that algorithm does. It defines what an expression is, what its syntax looks like, and it defines rules for computing the resulting postfix notation. So this is sort of independent of any particular way of implementing it. This is defining what that compilation process looks like. So let me go through an example of running this translation rule. So let's take our same expression here. So let's take another mathematical expression here. And let's apply these rules to compute the translation of this expression into postfix. So without giving you a specific strategy, we can compute these n's as producing the string representation of each of these leaf nodes. And e, when e is just a number, well, it just passes through the value. The value is identical. It's just a string. Because we're not trying to interpret the value here, we're just trying to turn this into postfix notation. We're trying to translate this into a different language. Okay, so let's look at the plus rule here. So when we have plus, how do we compute the value of it? Well, our rule says to concatenate the value of the left child, the value of the right child, and then the plus symbol. So what does that look like? What is the result? What is the string value when we compute the semantic value of this plus operation? What result do we get? Yeah, what is it? 9, 2, and plus. You see how that happened? So instead of trying to interpret the value, this rule just says, well, the value of this is going to be the concatenation of the left child, the right child, and the plus symbol. And so if we follow that rule and compute the value, we get 9, 2, plus. Looks like postfix, right? So let's see what happens when we then do this for the parent. The parent is this rule here. We get what do we get when we concatenate the left child, the right child, and the minus symbol for this parent rule? Well, what's the left child? The left child is 9, 2, plus. What's the right child? It's 1. And then we just concatenate minus at the end. And voila, we've got postfix notation version of this expression just by following this attributed grammar and its rules. Questions on that? Questions on how that worked? So this is really a compiler. It's translating between two languages. One is our infix arithmetic expression language to our postfix expression language. And you can see how you can build up the resulting program by following these rules to combine the children of each node into the final program. Questions on this? So I know this was a lot to take in, and I stumbled through some of it, so apologies for that. A lot to take in. You don't have to worry too much about the formal stuff. I just want to give you some background on parsing and compilation because you'll be using it when you write your compiler. But let me go over the exercise so that you'll be prepared for doing this. So we're going to be using the ANTLR parser framework, a really popular parser framework, which takes a grammar and generates a parser for us. So you can actually see the grammar here, and it looks a little different, but it's not unlike what we saw before. So we have an expression is a number, or an expression is another expression followed by an operator followed by another expression, or it can be an expression followed by an arithmetic operator followed by another expression, or it can be an expression in parentheses. So these rules, look very close to the rules we showed in class. ANTLR has its own syntax for it. But I've given you this. I've given you this code. You'll take that, and I've given you a makefile to build this. And the exercise is to hand write on your own without any help from anyone. Don't cut and paste code from anyone else. Don't use any OCR software. Hand write this file yourself. It's short. It's a short C++ program because I just want to give you some muscle memory and let you see how to use the ANTLR parsing framework. Just hand write it. You don't have to fully understand all the code, what all the code does. Hand write it. And then follow these rules for compiling and running your project. Submit it via Git, just like we do for all projects. And questions on this? Yeah.
Isn't that similar to the homework
homework, you mean writing an interpreter? Yeah, it's similar. It is. So, but before you just kind of hand wrote the you didn't have a parser. Here, because we have a bigger language, we're going to use this parsing framework to do it for you. You won't have to do the parsing yourself. So I just want to get you used to that parsing framework. What was I going to say? So yeah, this will just make sure you have C++ set up. And just, incidentally, these rules here, this enter, num, and exit operation, these correspond to these semantic actions that are on the right of the grammar. So we've got the grammar here, and for each of these grammar constructs, the C code will define a rule for how you interpret or compile that code. Yeah? No, it's not. No, you're very good. Yeah, it won't respect the order of operations. Yeah, that's right. That's right. So you can rewrite this grammar to build in the order of operations. Antler does something much simpler. It just applies the first rule that it finds. So that's why I separated into two of them. But that's, bigger topic for like parsing frameworks. But all right, everyone, have a good one.
When you said that the tree goes in like post order,